Good evening and welcome to everybody for today's program on the great universe. Today we have Bhavesh, Parekh from Orlando, from Portland, USA, early morning from there and evening time for us. I now request Mr. Mustaba Lokhandwala to please introduce Bhavesh, give the welcome to all of us, and please begin the program. Thank you very much.
Good evening, everyone from India, and good morning, everyone from US. We have people from both the places. It's a pleasure to introduce Bhavesh, Mr. Bhavesh Parekh, who amongst his multiple talents is also an entrepreneur based in Portland, Oregon, USA, where he operates several UPS stores. Apart from various talents, he is also an astronomer and a self-taught one, passionately pursuing his interest in astronomy and cosmology. He is neither a scientist nor a student of astronomy. He considers himself as a gatherer of knowledge. His hobby doesn't go very long, but it goes very deep. He purchased his first telescope, a 15-inch mirror, in 2017, and last year with his astronomy friends built a larger one with a 24-inch mirror. He has published a field guide for advanced amateur astronomers as a tool for finding deep sky objects listed in the astronomical catalog called as NGC, New General Catalog, which covers about 7,000 entries, which consist of galaxies, nebulae, and clusters. Ladies and gentlemen, it's a pleasure to introduce Mr. Bhavesh Parekh.
Thank you, Mustafa-ji. Good morning, everyone. Good evening. I just want to thank you, Mustafa-ji, Farooq-ji, and Sandhi-ji for introducing us all together and giving me the opportunity to come and talk to this wonderful group. I have seen several of videos, including yours, Mustafa-ji, on the universe, and the railway talk given a couple of months ago as well. Looks like a very nice group to be presenting to. So happy to be here. Good morning again, everyone. I'm Bhavesh Parekh, reaching out here from Portland, Oregon, a beautiful Pacific Northwest. Going to spend a couple of minutes, not too much on me and my background. I think Mustafa-ji covered that area quite well. I was born and raised in Bombay, and now currently I'm living with my family, my wife Reena, and my son Om in Portland, Oregon. I'm a BCom graduate from Sydenham College in Bombay and came to US in '82. Joined the IT industry, and just recently, about 10 years ago, started business, and now we're running a couple of UPS stores. My past hobbies have included just a lot of arts. Again, I'm self-taught there as well, just as a fun activity to do. When I was in India, obviously I was smitten like everybody else with Bollywood and cricket. So I went on to create some of the art based on that. And then after moving to US, I was introduced to the Native American, or as is known in India as a Red Indian, folk art. And then in the 90s, I also was introduced to Mithila Madhubani style paintings. And currently, as you know, I've been involved with astronomy and cosmology pretty deeply. Just wanted to show you guys a few slides of some of my past work. This is what I used to do instead of studying in college. These are the Native American people's portraits. This is some more Native American art. As you can recognize, these are some of my Mithila Madhubani Shaili paintings. And here are some Srinathji paintings from Nathdwara.
This is very good.
Thank you. And this is my most recent creation. this is the book that Mujtabaji mentioned a few minutes ago. It's a comprehensive field guide to the NGC. It comes in 4 volumes divided by different seasons of the year. These are my friends, my astronomy buddies. The gentleman on the left here is Steve Weiler. He's the one who designed and built this telescope for me. And some other friends of ours, Dave and Ed. We have a small place outside Washington State here, just north of Oregon, where we go and camp out for 3-4 nights at a time. And that's my home. That's my cargo van. I live and sleep in there during our trips there. It's quite beautiful out here. Very dark skies and good to observe from there. So let's get into the talk. Why am I giving this talk in the first place? It's safe to assume that there is this audience comes from many facets of life. You may have business owners, scientists, accountants, CPAs. So I wanted to design it so that it speaks to everyone, to a wide spectrum of audience. And it's my goal today is that I want to leave you with a perspective of the universe that you have never had before. The material I'm going to present is not necessarily new. Most people know about our solar system and our Milky Way. So the material here is not new, but I'm hoping that it will encourage you to learn more about our solar system, our galaxy, and ultimately the cosmos. So in short, I want to leave you with a taste of cosmos such that you are encouraged and empowered to seek more knowledge on your own. So the universe, it is very, very big and it's mostly empty. It's very huge. Things are far away and it's called space because it's mostly empty. Here is a very interesting and one of my favorite quotes by Carl Sagan. That says, astronomy is a humbling and character building experience. And in my pursuit of astronomy, I have certainly been humbled. The more I learn about the universe, the more humility it instills in me. Now, as far as character building, that's still a work in progress, I think. So, you know, the universe and cosmos shows us our place in the universe, and it tells us that we belong here. So as you listen here today to this presentation, I ask that you consider how what you learned today will affect your life and your actions. And that would be a good outcome from having been having seen this presentation. So before we get to the next slide, I want everyone to do a small experiment with me. If you can start with the thought experiment, close your eyes and imagine our solar system, the sun, the planets, the asteroids, all those orbiting around the sun, the stars in the skies. Just imagine that for a minute and see if this picture or this picture comes up as the vision. So these are the pictures that we see in most school textbooks, magazines, and most printed material that we have seen. The one on the left shows the sun and the 9 planets, or the 8 planets now. The one on the right shows the one on the left kind of shows the order of the solar system is correct, but the distances and sizes, relative sizes, are not quite accurate. The one on the right is shows the correct pictures, but again, the distances are not quite correct. So this is typical, and it doesn't tell the true story. So this is why I wanted to put together this presentation and try to retell this 2-dimensional story three-dimensional story using another two-dimensional method, this PowerPoint presentation. So I wanted to get a couple of things clarified here. We all are familiar with basic units of measurement: length, inches, centimeters, time, and numbers. And most of us deal with small quantities on any given day. But as we get larger and larger, we have normalized units, right? So instead of using inches and meters, we use miles and kilometers. Larger numbers, after 10,000, we go into lakh and crore, and 10 crores millions and billions. And it kind of makes things easier to understand. So instead of saying these statements, which are technically correct, but don't make much sense, we end up saying, using normalized units. My son is 21 years old, or distance from Pune to Bombay is not 150,000 meters, but 150 kilometers. So I wanted to introduce the concept of normalized units of measurement, because as we go out in the cosmos, distances get very, very big, and miles and kilometers stop making sense at some point. Another thing I want to just clarify before we go is measurements. I have, since astronomy, the numbers are very big. It doesn't really matter whether you round up or round down. So let's say, for example, a number that is 1,392,000, I'll round it up to 1.4 million. So if the numbers are not quite accurate, it's because I've just taken liberty to keep it simple and keep it an approximation. So I have a question for everyone, and just keep the answer in your mind, and we'll come to this answer in a few more slides. How large is our sun compared to the Earth, and how many Earths can we fit inside the sun if you were to put it in? Okay. The structure of the presentation is that I'm going to start where we are on Earth, in our homes, in our city, and then we'll start zooming out at the next higher level. And then we'll talk about that level, then we'll go to the next level again. So to start with, as I said, we are all in our homes, in a city, which is in a state, country, continent, planet, and the solar system. And let's talk about solar system now, and then we'll go to the next step, all the way to the end of the universe. So the solar system. So my presentation will have a scale at the bottom. You will see this black and white scale. And currently it's showing a scale of 1 million kilometers per notch. As we go away from the solar system and things starts getting larger, you'll still see this scale, the ruler, but the distances will change. And you'll know that in a couple of minutes as we move forward. So currently you're looking at a space that covers about 5 million kilometers. So we start with sun, putting it at the center, start at 0. Sun is about 1,400,000 kilometers in diameter, quite big. And if we start moving outside, away from the sun towards the planets, I'll start scrolling here. You can see the arrow. It just shows the direction that we are moving out into. So we click here, the next 5 million kilometers, there is nothing. Another 5 million, there is nothing still. Now we're going to continue scrolling until we scroll 7 more times to come to our first planet, Mercury. So now we are about 57 million kilometers away from the sun. And that small dot right there is Mercury. And it's so small because I have scaled this to be accurate. Now, how does a Mercury look in comparison to the sun? That's how small Mercury is compared to our sun. Mercury's diameter is about 5,000 kilometers. And let's start moving towards the next planet. We have to scroll 10 more times. So another 50 million kilometers to get to the next planet, Venus. Venus is slightly bigger than Mercury. And here it is again compared to our sun. Okay, we scroll another few million miles, and now at about 150 million kilometers from the sun, or 93 million miles, we come to our home, Earth. This is where we are, and that's the moon. And Earth is, compared to sun, is quite tiny. So earlier I had asked a question, how many Earths can fit inside the sun? Approximately 1 million or 10 lakh Earths can fit inside our sun. That's how vast and that's how huge our sun is. So now, as you can see, we are getting into much larger and larger numbers, 150 million kilometers. Most of us just kind of know this, it's a big number, but it doesn't really make any meaningful sense anymore. So we'll use kilometers for a few more slides, and then we'll convert to the next normalized units. So we've been using kilometers, which is equal to 1,000 meters. Now we'll introduce a unit of measure called astronomical unit, and that's 1 astronomical unit equals to 150 million kilometers. Why that number? Because that's the average distance between sun and the Earth. So distance between the sun and Earth is about 150 million kilometers, 1 AU. And light, which is the fastest traveling phenomenon in the universe, which travels at about 186,000 miles per second, or about 300,000 kilometers per second, will take 8.5 minutes to leave sun and arrive on Earth. Which means if the sun were to be extinguished at this moment, we wouldn't know until next 8.5 minutes that sun is gone. Okay, so we'll move to the next planet, which is Mars, at about 225 million kilometers. Mars, again, is very small. Here is a comparison to sun. And at this point, since numbers are getting bigger, we are going to go into the transition to astronomic unit. So Mars is at about 1.5 astronomical units from the sun. So we've covered 4 planets so far, Mercury, Venus, Earth, and Mars, and these are known as the inner planets or the rocky planets. And after we leave Mars, we come across the asteroid belt, and then we come to the gas giants, Jupiter and Saturn, and finally we meet our icy members of the family, Uranus and Neptune. So we start moving out again from Mars, and now we have to scroll 3 times the distance that we have already traveled to get to Jupiter. Jupiter, as you can see, is quite large compared to Earth and other planets we have seen, but still, compared to Sun, it's a fairly small object. Jupiter is at about 5.2 AUs. Again, AU is 150 million kilometers. And Jupiter has over 70 moons, satellites just like our moon, but 4 of them are well known. They are called the Jovian moons or the Galilean moons, and they are in order Io, Europa, Ganymede, and Callisto. So these are the 4 moons you can see on a clear night orbiting the Jupiter. If you have even a small scale telescope. Okay, next stop is Saturn at 9.5 AU, comparison to Earth and Saturn, and Uranus at about 20 AU, and Neptune at 30 AU. And finally, Pluto. A lot of us learned that Pluto was a planet, but it's no longer considered planet by International Astronomical Union. It is considered a body of its own. It's a Plutoid that belongs with other icy objects outside the solar system or the outer edges of the solar system. So let's take a moment to summarize the solar system objects and their distances. So now, as you can see, the ruler is there at the bottom, but now the scales are in astronomic unit instead of kilometers. And also the scale is logarithmic. Instead of 1, 2, 3, it's 1, 10, 100, etc. So 1 AU, we're going to see the sun at the beginning. Our Earth is at 1 AU. Saturn is at 10 AU. And heliopause, which is a theoretical boundary where sun's solar winds stop interacting with the interstellar medium. Then you have Oort cloud. This Oort cloud is OORT, Oort cloud, is about 2,000 to approximately 100,000 AU. This is where all the comets origin. All the comets we see, the Halley's Comet, Hale-Bopp, Comet Leonard, all the recent comets that I've been seeing, they all originate here and they start their journey towards the sun, and they come back in a long period because they are so far away from the sun. So that's why the comets, when they visit, it takes many, many years for them to come back. Okay. And if we continue moving out away from the sun, at about 276,000 AU. Again, this is the distance, 276,000, or distance between Earth and Sun times 276,000. We see our first star system, Alpha Centauri. Note that I had said it's a star system, it's not a star, because there are 3 stars in this system. Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. And Proxima Centauri is the closest star to our sun. And these stars are born and they start their life in a star cluster in a nebulae, and then once they grow up, just like humans, they move away from their families and they live out their life in other parts of the universe. So now, as you can see, the numbers are starting to get bigger even for astronomic units. So we want to now switch to the next normalized unit of measurement. So we started with kilometers, then we moved up to astronomic unit. Now we're going to go to the third one, light year. Light year is this big number, this many kilometers, rounded up to or down to 9.4 trillion kilometers, or about 6 trillion miles. This is the distance that's traveled by light in 1 year when it's traveling at 300,000 kilometers per second. There is one more unit of measure called parsec, and that is equal to 3.26 light years. Parsec, unlike light year, which is light year is a physical property of nature because that's how fast light travels. Parsec, on the other hand, is a calculated distance. It uses some geometry, but basically 1 parsec means 3.26 light years. And astronomers and astrophysicists use this 2 measures very frequently because that really covers large amounts of space. Okay, so let's take a zoomed out view of our solar system and the relative sizes. So the next slide, I want to show you the sun and all the planets lined up in their correct relative sizes, not the distance, but just the sizes. So again, as you can see, sun is quite huge. That third dot is Earth, our home. If you take all the mass in the solar system, 99.9% of the mass, the stuff, is in the sun. 0.1% constitutes all the other planets, moons, asteroids, comets in the system. So now we're going to move up to the next level. As you can see, we came from our home to solar system. The next stop in our trip here is called local bubble or local neighborhood. So again, my ruler back here, now the scale shows 60 light years. Again, 60 light years, light year is 9.4 trillion kilometers. So this is about 70 million or 700 million kilometers space here. If we put our sun in the center, and this is again just for convenience, sun is not the center of our neighborhood. It's just one average star that belongs in the neighborhood. And obviously this size is not to the scale. So these are some of our closest neighbors. As you can see, the sun is in the center here. Alpha Centauri, that's the closest star system. If you can see, this Pollux and Castor, the two stars in Gemini. We have Vega, one of the brightest stars in the sky. Sirius, the brightest star after sun in the night sky, is Sirius, and that's fairly close to our sun. So this is our local neighborhood. A large number of the stars, I just want to take a minute, have Arabic names. As you can see, Altair, Ras Al-Hag, Denebola, Deneb. The reason is because the people of the Arabian Peninsula about 1,000 years ago or earlier, they were quite advanced in astronomy, and they discovered, and because they discovered the stars, they had the right to name the stars, and whatever names they called continued to be the names of those stars. Some of the more famous ones that astronomers look for are Aldebaran in Taurus, the bull, Altair in Aquila, the flying eagle. And you can see some of the names make sense. Altair or Tir, like an eagle, arrow. Ras Al-Hag is in Ophiuchus, is a snake charmer. Deneb is in Cygnus, the swan. Deneb means tail. And Denebola is also the tail star in the constellation of Leo. So this is our closest neighbors, very small distance, about 60 light years. Let's zoom out to the next level. The next level is the spiral arm. As most of us know, we are a part of a galaxy, Milky Way galaxy, which is a spiral galaxy. And any spiral galaxy will have arms coming out of its center going in circle. So we belong to one of the minor arms, not even a major arm. It used to be called a spur, but now it's called an arm. And that spiral arm is the Orion Cygnus arm. So this arm is about 10,000 light years across and or long, and 3,500 light years across. As you can see, the scale has changed now. This is, the screen will now show an image of the space that spans 10,000 light years. Again, sun is at the center of the image, and here is the image of our Cygnus Orion arm. The area is this section. This is the Cygnus Orion arm. These are some of the other arms that I'll come to in just a minute. And you can see This is not the precise location of the sun. Sun is somewhere there in the middle. And obviously it's not drawn again to scale, because this area alone, this Cygnus Orion arm, contains 800 million stars, or in the Indian terms, it's 80 crore stars, right in this space here, in the distance of about 10,000 light years. Zoom out again, and now we come to Milky Way. We're going to get a view of the Milky Way, our home galaxy. The distance, the space shown will now show 100,000 light years. That is the span of our galaxy. It's a disk, it's rotating like that, and so it's about 100,000 light years across, and it's 2,000 light years deep. So here is the image, a little bit more zoomed out image. If you remember, this was the Orion arm where our sun is. And now we can get a better picture of the Milky Way with the central bulge and different arms coming out of the center. So I want to take a minute to go through these different features in our galaxy. This is, of course, an artist's impression of our Milky Way. Nobody has ever gotten out to take a picture of it because it's way too distant from where we are. Again, in space, I want to introduce another concept that's called cosmological principle, that in space, there is no direction. There is no special direction. There is no special place. Everything is the same as everywhere else. And it's called cosmological principle. It says the universe is homogeneous and isotropic. Homogeneous means that everything looks the same everywhere. And isotropic means there is no special direction. A lot of us practice feng shui or vastu sastra, which talks about the north and east and different cardinal directions. But when you're out this far in the space, there is really no special direction. So let's look at different parts of our galaxy. So this is a picture without any identifying markers. We start with the center. This is called the central galactic bulge, or a bar, as you can see. So our galaxy is a spiral galaxy, but it's a barred spiral galaxy. And just like any other galaxy, the central area of the galaxy, our galaxy, contains a supermassive black hole. All galaxies center have supermassive black holes. When I say supermassive, it really is very, very massive black hole. The one in the center of our galaxy contains the mass that is equal to 4 million masses of our sun. So that one black hole, supermassive black hole, is equal to 4 million of our suns, or 40 lakh of our suns. These two arms away from the center, they're called the 3 kpc arm or 3 kiloparsec arm. If you remember from the few slides back, kiloparsec means parsec is 3.2 light years. So 3 kiloparsec is about 3,000 parsec. So the distance of these arms are 3,000 parsecs, or about 10,000 light years. And there is an arm that's near, and there is a 3 kpc arm that's far. Near and far because they are in relative position to our sun. Our sun is right here, about 25,000 light years from the center of the galaxy. Next, we look at Norma arm, which is starting here and going across. I'm going to switch to a pointer if I can.
We can see your pointer.
Yeah, I'm going to get the laser pointer here. Thank you. Okay, so this is the Norma arm. Next is Scutum Centaurus arm. then Carina Sagittarius arm, then our own Milky Way, Orion Cygnus arm. Perseus arm starts at the bottom here. And then we have one more arm called the outer arm, and even more newer outer arm lies at the far reaches of the galaxy. So this is our Milky Way and different components of the Milky Way. That's our home galaxy. The age of the Milky Way is about 12 billion years old and contains about 10,000 to 40,000 crore suns, stars. They're all different sizes. Some are big, some are small. Our sun is kind of on a smaller side, as big as it is. Most of the stars are smaller than our sun, and they're called the dwarf stars. Very few are bigger, and they're called giants, supergiants, and hypergiants. You say hypergiant, what is a hypergiant? So just to get a perspective of what a hypergiant looks like. This is a star called UY Scuti. This is a star in the constellation of Scutum, the shield. And that's why it has got this Latin name Scuti. And if you imagine this sun, you're looking at just a small section of the sun, of this star, Scuti, and get a sense of how big it is. I'll show you the sun. That is our sun compared to this hypergiant sun star called Scuti. Okay. The UY Scuti is about 1,700 times the radius of our sun, and it is about 5 billion times the volume of our sun. And it's very close to our neighborhood, about 9,000 light years. So we're going to zoom out to the next level. But before that, I want to pay an homage to this gentleman who's sitting on a very large telescope in 1923. This is a picture of Edwin Hubble. And he discovered in 1923 that we live in one of the galaxies. Until 1923, we humans believed that our galaxy Milky Way was it. That was the entire universe. But with this one picture that you see on the right-hand side, there is a little story behind it. I won't get too much in the detail, but basically he found what he thought was a nova. And then he realized his mistake and he crossed it out and said, VAR, it's a variable star. And that made him recognize that this object, the Andromeda Nebula, as it was known at that point, was not a nebula in our own Milky Way, but it was a galaxy of its own. And with that one picture, our universe exploded into billions of galaxies. So until then, our universe was one galaxy. Now we are just one small, tiny galaxy in a sea of billions and billions of galaxies. So this is Edwin Hubble in his 100-inch Hooker telescope in Mount Wilson. So now we're going to zoom out even more. As we fly away from Milky Way and get a wider perspective, now we come to an area that's called local group. Local group is a group of galaxies that are our closest neighbors. And now we're going to see space that spans about 10 million light years. So here is an image of our Milky Way galaxy. And these are all the galaxies in our local group. It contains about 50 galaxies. Largest of them is Andromeda. Then we are the second largest, Milky Way. The third largest is a Triangulum galaxy, and rest of the other galaxies are classified as dwarf galaxies. Someone actually was musing that if there are that many dwarf galaxies, then maybe they are normal and we are giants. It's a matter of perspective. I want to go back the slide and give you perspective again. So this is the Milky Way, Andromeda. The distance between Milky Way and Andromeda is about 2.5 million light years. And these two galaxies are actually on their way to meet each other. So if you are around in about 4 to 5 billion years, you will witness a merger of these two galaxies. But until then, we are in our own space. There's this beautiful large and small Magellanic Cloud. Someday I hope to travel to southern skies and see them. And there are other small dwarf galaxies in our local group. Next zoom level out is what considered a supercluster, and that's a cluster of galaxies. And as you know, again, our distance ruler is updated now to show a view of 520 million light years. This view will show about 100,000 to 150,000 galaxy. And I don't know if you can see, but local group is right there. One of those dots is our local group that contains 50 galaxies. And this is a view of various superclusters and clusters in our local supercluster area. So let's see. Now I want to, so this is our local supercluster, but I also want to talk about another supercluster a bit closer to home to Farooq Bhai and Mujtaba ji in Pune. This is called the Saraswati supercluster. A few of our scientists, astrophysicists in Pune discovered this supercluster using Sloan Digital Sky Survey data, which is, by the way, the same data I have used, the pictures, images I've used in my book come from this digital sky survey. This Saraswati supercluster is about 650 million light years across. It's 4 billion years old and contains about 200,000 galaxies. Here is an image of the supercluster Saraswati. Next up is local supercluster, which is a cluster of superclusters, and it spans an area of about 2 billion light years. And this is what it looks like. Our supercluster is somewhere here. And as you can see, this is pretty large perspective of the universe. And they're just clouds and dust. They're just floating everywhere. There's nothing special. They all look alike. They all look the same. Next level up, we're almost towards the end here, and we come to what we know as the observable universe. This area of the universe is about 93 billion light years across and contains trillions of galaxies. And this is an image of our local observable universe. As you can see, there is a small dot here, local supercluster containing 200,000 galaxies. This is quite vast. So observable universe is 13.8 billion years old, and it contains 2 times 10 to the power of 23, meaning 10 followed by 23 zeros. That's how many stars there are in the observable universe. Each of the stars we now know contains planets, one or more planet of its own. To get a perspective of how large this number is, I'll do another thought experiment here. If you imagine walking on a beach and just bend down and pick up a pinch of sand, Blow away all the sand and just keep one grain of sand in your finger. Look at that sand, that one grain of sand, very tiny. Now imagine how many grains of sands are there on that beach. Now imagine how many grains of sands are there on all the beaches of the world. If you can imagine that number, then know that the number of stars in the universe is bigger than that number. There are more stars in the universe than there are grains of sand on all the beaches of the world. So very, very large place. So I've been saying the word observable universe as opposed to the universe, because observable universe is still a small part of our universe, entire universe. There is a part of the universe that is so big that we'll never be able to see it, even when the light has left that part of the universe coming towards us, because it's so far away that light will never reach us and we will never be able to see it. So that's a cosmic horizon beyond which the universe lies, which is even bigger and larger than the observable universe. There are some estimates that the actual universe may be hundreds or thousands of times bigger than the observable universe itself. So the observable universe is about 13.8 billion light years across. And our final step is the universe. And we don't know how many light years across it is. We don't know how many galaxies there are. And we will never know that fact, because it'll forever be out of our reach. So this is the end of the universe. Now we come back to our home. And before we return, I want to show one more image. Earlier, I showed the image of Edwin Hubble, the man. Now I want to show you an image of a small part of the galaxy, of the universe, that was taken by Hubble, the space telescope. This is an image. At first, it seems like in this image, there are lots of stars. Technically, that is true, but they're really, I can notice 1, 2, and maybe 3 and 4 stars. Everything else is a galaxy. Each of these dots is a home to billions, tens of billions, or hundreds of billions of stars. In this picture alone, you can see approximately 10,000 galaxies. This picture shows a very, very tiny part of the sky. If you can imagine taking a grain of rice, putting it in your fingertips and holding it at arm's length, the amount of sky that will be covered by that grain of rice shows this many galaxies. And if you multiply it by the total amount of sky, you get a number, something that runs into trillions. This is how we know that there are trillions of galaxies in the universe. So I want to get to the next step here. The universe, what is it made up of? We can see things, we can see stars, we can see planets, we can even see on a cloudless night, Milky Way that contains dust and other periodic table elements. Let's call that ordinary matter. That's what we are all made up of. So ordinary matter is what the planets and asteroids are made up of, what stars are made up of, and the gases and dust. Now, if you take the entire volume of the universe, this component, the ordinary matter, consists of only 4.5%. All the planets are less than 1%, less than 1/10 of a percent. all the stars in the universe make up about 0.5% of the mass of the universe. The gases and dust make up another 3.5%. So this, everything we see, we recognize, is only about 4.5%. There is another type of matter called dark matter, and that takes up another 24% of the universe. So combined, the matter, ordinary matter and dark matter, makes up about 28% of the universe. That still leaves about 72% of the universe. And that we have discovered is something called dark energy. Dark matter and dark energy, we don't know what they are. Scientists don't know what they are. They're just a placeholder. We do know that 20% of the universe is some sort of matter because of its gravitational interaction with its surrounding. And the rest of the universe we call dark energy. We don't really know what it is. And that's 72%. And this dark energy is what we believe is responsible for the expansion of the universe. Universe is expanding at about 78 or 73 kilometers per second per megaparsec every second. So universe is growing, and that is happening because of the dark energy. So to give another perspective on this number of what makes up the universe, here is a little diagram. If the whole rectangle was the universe, this part represents the dark energy, dark matter, all the gases, dusts, stars, all the stars we see in the night. And this small line here represents all the planets of those trillions and trillions of suns. So now we know what the universe is made up of: ordinary matter, dark energy. What are we made up of? We humans. We are made up of a small fraction of the stuff that plants are made up of. Now, as we know from the periodic table of elements, the hydrogen, oxygen, carbon, nitrogen, the various elements in the universe. But if you were to look at the elements by abundance, by the number of atoms, you will see that the hydrogen has the most number of elements in the universe. The next most abundant element in the universe is oxygen, then carbon, nitrogen, and then the element called the other. Everything else fits into the last category. So universe is made up of mostly hydrogen, oxygen, carbon, and nitrogen. What are we made up of? Humans. 60 to 70% of our body is made up of water, and water is H2O, hydrogen and oxygen. And if you analyze all the atoms in our body, you will find that by abundance, our bodies are made up of hydrogen, oxygen, carbon, nitrogen, and other. 1-to-1, there is a ratio of the elements in the universe to the elements in our body by abundance, not necessarily by volume, but by the number of elements that are in the universe. So we are made up of stardust. We are at once very small, insignificant, yet in a meaningful way, we are connected to the cosmos. So you can say that not only are we in the universe, but it's more important that the universe lives within us. So we come back to our home. This is where we are, the blue marble, pale blue dot. This was a picture that Carl Sagan convinced NASA to take of our Earth as a Voyager telescope spacecraft was leaving one of the planets, I believe it was Uranus or Saturn. And this is a picture. You can see the sunbeam. I don't know if you can recognize our planet. There is a small dot right here. This is Earth. So Carl Sagan had this quote, and I'm going to read that to you. So look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was lived up their lives on a mote of dust suspended in a sunbeam. The earth is the only world we know so far. And to me, as Carl Sagan said, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we have ever known. So in conclusion, I want to give a few of my own thoughts that even as we live on this small mote of dust in the vast cosmos, so abundant with matter and energy, and yet as human beings, we have continued to find ways to subdivide ourselves into smaller and smaller groups. We divide ourselves as man and woman, young and old, Hindu, Muslim, Sikh, Christian, Congress, BJP, Democrats, Republicans, black, white, rich, poor. We have decided so many ways to create an us and them wall. I want us to consider that there are really no them. It's all us, the human race. And we need to work together. We need to cooperate. And that is the only way to move forward. That is the only way for us, the human beings, our species, to survive and prosper. And that brings to conclusion the main part of my presentation. I want to again thank you all for your precious time, your attention. Really appreciate Jnana, the opportunity to come and talk to this wonderful group. And I have one question before I hand it over to Mustabaji, that now that you have perspective on the cosmos, how do you see this affecting your life and your actions? What are you now interested in learning, and how will you go about doing that? At the end of this slide, I have listed numerous resources that I have used myself to educate myself, and I'll leave it here, and I'm sure it will be on your on the recorded slide, so you can revisit these slides, and I hope you use those resources for your own knowledge gathering. Thank you.
Thank you, Bhavesh Bhai, for a fantastic presentation. I must say that your presentation skills are world class. Beyond the universe. They are beyond the universe. So I now invite Mustafa. Can you please unmute yourself and put on your video so that you can take over from here? And please invite the panel to speak.
Good evening, everybody. Bhavesh, it was an amazing presentation.
Thank you.
And I am sure it is an eye-opener for all of us. And yes, there have been a few questions from this thing. So one of the things that I personally have realized with the study of astronomy is that we are so insignificant on the scale of the cosmos. And we think of ourselves as the masters of universe, but we really are not. And one question that somebody had asked was, about this thing, light coming from a black hole. You had shown a black hole, this thing, and it is from Manoj Kumar. If it's a black hole, light shouldn't be coming out. How come it is appearing bright? Sandhi has asked that, answered that question, that it is light doesn't come from the black hole, it comes from the surrounding areas. Would you like to elaborate on this?
Yes, that's a good observation because black hole is such a massive object that its gravity will hold on to anything. It's so strong that nothing can escape a black hole, not even light. So yes, a black hole will never emit a light as we see in photons. Now the picture we saw earlier, again, remember that was an image. It was a rendering, and it was showing the what seemed like light. Um, it's just to represent how much energy is in that particular area because it contains so much mass of 4 million stars. So yeah, if you looked in that space with a telescope, you will see pitch black. You will not see it. Now you can see using different telescope, not optical telescope, but X-ray, gamma ray radiation telescope, radio telescope, you can see different spectrum of the electromagnetic spectrum. And that is kind of what's demonstrated on that picture. But you're right, yeah, black hole will not emit
I
any
have
light.
another question from my side. You mentioned that the age of the universe is 13.8 or so. There are different values for that.
Yes.
So many years, which means that the earliest this thing, light, would have reached us. We can see 13.8 light years in either direction.
Right.
How come is the size of the observable universe 60 billion light years?
It's very good observation. I had a slide earlier. I kind of jumped over it. So to rephrase, when we see light from an object, it really is, we are seeing that object as it was when the light left it. So if an object is 1 million light years away from us, that means the light left that object million years ago and is just now arriving at us. So when we see that object, it was as it appeared a million years ago. Now, if you take the same concept and say the universe began 13.8 billion years ago, that means if the light left the beginning of the universe and is just now arriving here, it should be 13.8 billion light years away. But we know from observation that the observable universe is actually 92 billion light years across. So why this discrepancy? That has to do with another concept I spoke about earlier called the dark energy. See, universe has been expanding from the beginning and it continues to expand and it will continue to expand. So even though the beginning of the universe, I don't want to say center of the universe because there is no center of the universe. Right. I'll say the beginning of the universe is 13.8 billion years away. The universe is still 92 billion. The observable universe is 92 billion. We don't really know how big the actual universe is. So right. That is a discrepancy that is explained by dark energy and the expansion of the universe.
Yeah, I think Apurva has a question. Apurva, over to you.
Yeah, I'm getting my mind wrapped around this. It's going to take me some time to understand it. My question is that since we know so much about the universe, are we observing, like you said, there were two stars which are going to collide in so many billion years. So what is our chance of survival? Is there anything coming our way which you know but you don't want to talk about? Is there something like that? Because we get films all the time that ye aa raha hai, wo aa raha hai, something's going to wipe us out. Right. So is there something that we should be worried about? And my second question is about intelligent life. Anyway, if I could ask you all the three questions, is that our life is not an accident. Like you said, that these elements is how the universe takes place. This is how human. So obviously, science dictates that the probability is very high that there will be intelligent life somewhere else. Okay, and since oxygen is the second most important element here, so what are your thoughts about that? And what is the furthest object that you have observed with your telescope? So 3 questions.
Okay.
Yes, please.
Gotcha.
Thanks.
Yeah. So you had 3 questions. The first one you asked about is something coming at us.
Yes.
So earlier I had mentioned that we are moving towards the galaxy Andromeda.
Yeah.
So our galaxy Milky Way and Andromeda galaxy, by sheer gravitational forces, are moving towards each other. Now that is going to happen in about 4 billion years. So humans for now are safe from that. Yeah. Even if the merger was happening now, it would be fine because it wouldn't be a collision or explosion of stars, because the space is so vast that even when the 2 galaxies merge, the stars are not going to collide. So to give an example, how small the stars are and how distant they are, imagine 2 stars as 2 flies, and these 2 flies are 72 miles apart. So when the 2 galaxies merge, there are hundreds of billions of stars coming together, but the chances of them colliding are very minuscule. So that takes care of the galactic merger. The second part of that first question was, is something coming at us? Yes. So, universe just has, our solar system has many objects. They're coming from the Oort cloud, the asteroids are coming at us. So yes, there are many objects that do pay us a visit, and sometimes a little too close for comfort. So yes, there are agencies like NASA and other international government agencies. They do have programs in place to identify these objects and try to mitigate their encounter with us, so to speak. So that is always in always in the works.
The second question was about intelligent life.
Yeah, there was one more question. We have with us Dr. Sabyasachi Chatterjee, who's an astrophysicist among our audience. And he has made a very interesting observation. I would like to invite him to make his observation publicly.
Thank you.
Dr. Saab, you can speak. I've requested you to, Dr. Saab, you can speak. Chatterjee sir. Mr. Chatterjee? Mr. Chatterjee said is that on an average, our galaxy has only 1 hydrogen atom per cc. Now, I don't know what that means.
1 cubic centimeter.
Cubic centimeter, yeah. This only Dr. Saab can answer. Is he available now?
Yeah. The idea being is that the density of the universe is very small.
Yeah.
The things are spread out very much. There's a lot of empty space between objects, atoms, and everything.
Right.
And that could be the dark energy, as Bhavesh was.
So I mean, even the atoms and stuff that we are made up of, it's mostly empty space. When you really zoom down at the atom level, you'll see the nucleus and the electrons hovering around it. If you were to take, there is an example somewhere that if you were to take all the mass, all the people on Earth, and you took away all the empty space and left just with the nucleus, the quarks, and the electrons, that mass would come to a size of an apple. So that's how much empty space is in the universe.
Acha, Mustafa, can we request now Sandhi to speak? He has been
please,
so many messages. Bapre, Sandhi.
Sandeep should have the last word, I suppose.
Yeah, I also like to have Leslie say something.
I I just wanted to say, Bhavesh, I'm so proud of you. You have done an excellent job of presenting to put life in perspective and how you navigated from purely physical knowledge of the universe to a sentimental message for us. I mean, we are still fighting a Ukraine war right now, and it's everything looks so stupid compared to our insignificance that I wish all the politicians around the world have that perspective that and in the span of the life of the universe, even if you live 100 years, it still is nothing. I think I just wanted to ask one thing, and I have asked this question to many people. I still have not gotten a satisfactory answer. And the question is, we always say the universe is expanding, as in capital IS. And all our calculations of dark energy and dark mass are based on that concept. But it's like, and I often like to say, what if I were to tailor my clothes based on measurements I took when I was 2 years old and tried to fit them today? Because we really don't know, to be honest, whether the universe is expanding. All we can say, it was expanding in the past. So the question is, as you aptly said, the light is reaching to us, that's 13 plus billion years old. So we really have no idea. And the only worry I have, it's all our calculations of presence of dark matter and energy are based on the concept of is expanding and not was expanding.
Correct. Yes, it is. It is continues to expand, and it will.
But we don't know. We don't know if it continues to expand, because we'll only know if it is continuing to expand. Another 13 billion years after.
Yes, that's work in progress by people who are a lot more smarter than I am.
So one more question before we go. You said, and I'm just asking this for a general public here as well. The comets are formed from the Oort cloud.
Yeah.
The question is, how do they gain momentum? Coalescing particles and ice particles and back through the process of gravitation is different than gaining momentum towards the sun.
That's about the extent of my knowledge on that, Sandhiji, that it is that the sun's gravitational forces are what's primarily responsible for it. If there is more to it, I'm not aware of that.
Yeah. Okay, I'll keep quiet. I can always ask you questions anytime during the day.
Sure.
Leslie wants to ask a question.
Yeah, there is an observation that our solar system revolves around the edge of the Milky Way every 250,000 years.
Correct.
So we are presently at a place where 250,000 years ago there was the dinosaurs who ruled the earth, walked on the earth. Your comments. Your comments about this revolve, especially about the solar system itself revolving around the edge of the Milky Way.
Okay, so everything in the universe is moving. Nothing is static. Earth is moving around the sun, and sun is rotating around the Milky Way center. And the Milky Way itself is moving, and the clusters are moving. So everything continues to move, right? The time it takes our sun to go around the galaxy, I believe, if I'm not mistaken, it's actually 250 million years, not 250,000 years. So it's 250 million years. And I'm sure. I'm sorry. What was your question on that observation? We can't hear you. You're mute.
You're muted, Leslie.
This is an observation that this is just like the sun, just like the earth moves around the sun every 365 days. so
Right.
does the entire universe, and sorry, entire solar system also move around the Milky Way.
Correct. Yes. Yes. Everything is in motion all the time.
So, but
So
this
we
is
will
a
never
standard,
be.
this is a standard fixed.
Yeah, Sandhi
fixed
has
time
pointed out,
motion.
Leslie, that we have made 19 rotations around the center of the Milky Way so
Yes.
far since Earth's creation.
Correct. Correct.
Right.
The other thing is that whatever the Earth is a transition. The sun is not forever,
Correct.
because it has got nuclear energy. It has got energy which how much ever it is, it is not forever. It is
Correct.
not. It has to end at some stage.
Correct. Yeah. So stars, just like human beings.
Every star, not only the star.
Yes. Every star, like human
And the
beings.
sun is an average star. It's not a massive, huge star. It's an average star.
Correct. Correct. So our sun is burning millions of tons of nuclear fuel every second. And even at that rate, it will still continue to burn that fuel for another 4.5 billion years. And once it's spent, it will spill all its fuel, the higher fused elements, into the space, and the gravity will bring those elements together again and form a new star. So our sun is actually a second or third generation star. It was born out of the ashes of its predecessors. As a matter of fact, we were talking about the elements in our body. So if I look at my left hand and right hand, the hydrogen in my left hand may have been formed, or oxygen and carbon formed in a star 100 light years this way, and the carbon in this hand could have been formed in a star 1,000 light years this way. The gravity brought it together, and now those two elements are part of me. It's amazing.
Okay, Dr. Chatterjee would like to speak. Chatterjee sir, can you please add to today's conversation?
Yeah. Actually, it provokes so many things. Yeah, that plenty of discussions can actually take place. And let me tell you in a little sequence, one by one. First of all, distance scales. The way you introduce the distance scales, but I would go back a little bit, and I would say the most accurate distance that was measured was the diameter of our Earth by Eratosthenes in Egypt. It is a fascinating experiment.
Yes.
And it was still so accurate.
Yes.
That is one. And of course, later a similar way was repeated by Alberoni in the deserts. So I think distance scale, mass scales, and all of them are so coupled together.
Yes.
But we knew nothing of these till about 500 years ago, until Newton's laws came, until Kepler's laws came. So all our knowledge with the level of accuracy that you're talking of, our fundamental science came only 400 years ago also. And the other thing that, yes, you referred to the distance scale of our galaxy. It is only 100 years old. We never knew it. As you said, you showed the pic. Before that, there was what in astronomy we call the great debate between Curtis and Shapley. Okay, anyway, you referred to it and you told. And finally, last thing that I would like to say, all this that you were talking of, hydrogen burning, helium burning, final state of stars, etc. We could have never have known that till about 70 years, until the fusion was understood by us.
Yes.
So by taking just one journey, we can get into different directions. And lastly, I would say, you began by saying that Arabs knew astronomy so well. I mean, astronomy means positional astronomy. And that is because theirs was a very advanced agricultural society. On the banks of Tigris, Euphrates on the one hand, and Nile on the other, and they needed these star charts for their calendar making and also checking the season change when the plow has to be brought out. Anyway, it is very fascinating, and we will continue, I believe. Yes.
Yeah.
I have an idea to begin or to start a series which can be called, you can consider this also, all participants, whether it's possible. It is called Science Ki Kahaniya, Vigyan Ki Kahaniya. Stories.
Yes.
Stories. And stories may not end. It may become like Mahabharata. Okay. You start at one point, it goes in another direction. Just consider whether or Adda. It is just a concept I have. Okay, thank you very much. And thanks a lot for sharing the way you have learned things.
Yeah.
Yes.
So,
Thanks.
I would like
Thank
to
you, Dr.
invite-
Chatterjee. Appreciate your comments. Thank you.
I would
Maybe
like
you can be one of the speakers in a short while.
Someday, but I will like to go in the form of Vigyan Ki Kahaniya. Okay.
a series of talks.
Yes, so that others will find out. So the others will find out how things were found out.
I would now like to invite Dr. Eraj Barucha. Please speak, Dr. Saab.
Bhavesh, absolutely fascinating.
Thank you.
One thing that every time I contemplate the stars, and these days you don't see so many stars in Pune, it's so badly polluted. But when you consider that and you see the Milky Way,
right?
We're all made of the same sort of matter in different compositions, probably. And I cannot imagine that with so much material there in this enormous space, are we really the only living things that are there? How do you feel about this?
Well, I mean, yes, as somebody mentioned earlier, we are not made up of any special matter. We are made up of the same stuff that the universe is made up of. And it's in anywhere we look, we find the same amount of stuff. So it is not unlikely that there is life out there. We just don't know yet. We are looking. There's a lot of missions out there, the Kepler mission, TESS telescope, and now with James Webb that just went out on December 25th. We are in a golden age of astronomy. Just last 100 years, how far we have come from just one galaxy to 10 trillions of galaxies. We're just at the beginning of our learning journey. I would love to come back in 100 years, 200 years and see what humanity, if we are around, if we haven't killed each other, what we have learned. It will be just fascinating to see what we have learned 100 years from today. But yeah, there is a good chance there is life out there. There has to be. Otherwise, it would be such a waste of space.
Yes, that's a good way to put it.
Bhavesh bhai,
yes, sir.
Eraj is a surgeon by profession.
Okay.
He is presently 78 years old. And last week we did a presentation on Dr. Salim Ali. And, he writes books, and he doesn't write small books. He writes this book, You can see this book.
Oh my gosh.
This book. And he says
Wow.
this is the mini version of the book.
Wow.
He says that he has written the book 3 times the size of this.
Wow.
मेरे को उठाने को भी नहीं आता, मेरे को muscles आ जाएंगे. So, and he has worked so much on nature and wildlife and things, and what you have done, visualizing the cosmos and the cosmology. Our Dr. Saab here in Pune is a surgeon. He is a nature lover. When he was 7 years old, Dr. Salim Ali took him on his motorcycle to see the birds.
Wow.
And he has written a wonderful book. Now he's written a story. He has sent me to read it. I have to read it, and then, he is just too much. So when he speaks, I always feel humbled,
But Bhavesh, thank you very much. Of course, your mind to just this incredible universe.
Yes. So, Bhavesh bhai, I think Mustafa and Sandhi and Apurva, with your permission, do you think any more questions, anything more to add?
So one last question. What are the furthest object that you have observed?
Oh, yes.
Yeah.
Apurva, I'm sorry,
Yeah,
I was
yeah.
coming back to you.
Yeah.
I think we answered your second question about life.
Yes, I got it.
The farthest objects I have seen, I would have to say about 300 to 400 million light years ago, away.
Okay. All the planets, Jupiter, obviously, that's.
Yes, the Jupiter and Saturn I can see very easily in summer, especially.
Okay.
But this object I'm talking about is a galaxy. Okay. It's one of the NGC New General Catalog galaxies, and it is close to 300 to 400 million light years away. So that's probably my observation so far.
And by human beings, what are the furthest object that seen from the Earth?
If you consider Hubble telescope, right? I think we have seen galaxies that is just 400 million light years old, okay. Which means it would have been about 13.4 billion light years away in nominal terms. But with the expanding universe, it's even further out.
Okay.
But Hubble has seen, in that image I showed you, there was one red dot that is supposed to be a galaxy that's about 300 to 400 million light years after the Big Bang.
Okay, thank you so much.
We are having two scientists having a conversation on the chat group, Dr. Eric Barucha and Dr. Chatterjee. And
okay.
Anyway, Mustafa, I hand it over to you now. Please.
Yeah, Bhavesh Bhai has been such an amazing presenter. I am, thrilled and what I would say overwhelmed by his presentation. It has touched our hearts. It is such a dry subject, astronomy, but he has made it into a heart-touching exercise. He has made so many things. And the amazing part of it is he has written 4 volumes of that book where we has written about so many NGC objects. And those 4 volumes, about 7,000 of these things he has presented there, and which can be used by people to look for them. Where to look and how to look is this thing. Thank you very much for joining us today and getting up early in the morning and connecting with us. It was an amazing journey to be with you. We love to hear from you again in the future. Thank you very much. Thank you, Farooq, for organizing this too. And thank you, the audience, for everybody for being such an active audience. We appreciate that.
Bhavesh Bhai, before going, if you have your book next to you, just show us the book that you showed me 3 days back, what you have made, if it's possible.
Yeah, if you can, please.
Sure.
And Mustafa, jara explain karo kya wo book hai, to after.
Yeah, there is a concept called as, a lot of people who were searching comets and other things, they require.
This is
the volumes. And
these are some of the pages from, these are all pictures of galaxies and clusters with information about them.
So how does one use this book? I mean, if I have the 4 volumes.
That will be another program.
Okay.
That'll be another program, yes.
Yeah, he has covered almost 7,000 such entries, and it is very useful for comet hunters and others to use it and understand it so that new discoveries of comets can be made. Mm-hmm. So thank you very much, Bhavesh Bhai. It was.
I have a question. I have a last question. Those who have seen Kashmir Files, there is a nebula that comes up. Do you guys know what nebula it is?
No.
So the moment I saw it, I said Trifid Nebula.
Mm.
And right in the darkness, my wife opens up her cell phone to make sure I was indeed right on. But if you ever see that movie, the initial parts, there is a Trifid Nebula.
It's a beautiful nebula.
Yeah.
Just like a flower.
Yeah.
Yes.
Yeah.
Okay, with permission of everybody and Sandhi and Mustafa ji, thank you very much for being there. And Bhavesh bhai, thank you very much. And
Thank you all.
Yeah. Have a nice day.
Yes, sir, we will. You guys as well. Good night.
Take care.
Good night.
Bye-bye.
Good night.
I would like to tell everybody that this program will be on YouTube on Monday evening. It is already there on Facebook. I'll be posting the link of the Facebook after the program. Thank you very much.